Hi, my name is Fabian Trumper. I'm a Senior Product Manager for PMC Sierra, and I'm here to talk about our Flashtec NVRAM drive that we're launching today. I'll be talking about the problem space that we're addressing, some of the key benefits and features of the product, and some performance that you are going to get from this product. Let's take a look at the key features of the product. What you see here are the memory capacity. We have 16 gigabytes, 8 gigabytes, and 4 gigabyte capacities for this solution. Here is the flash module, the flash backup module, which is used to back up the memory in case of a power failure. In the middle here we have our Flashtec NVMe controller that is used to manage the whole solution and provide also the by 8 PCI Express interface towards the host. So altogether a very high performance solution. So if you look at any storage system today, what you see is what you have here in this slide. You'll have the data coming in from the external interfaces. You'll have the storage engine that's doing the processing of that data. And every storage engine will have its own key feature, whether it's deduplication or compression, encryption or mapping. But they all have the same problem. They have to deal with the data and process the data, while at the same time acknowledging it and providing an acknowledgement to the higher level application. And for that, all storage systems will use some kind of a write buffer cache to acknowledge the data as quickly as possible and let the application move on with its own tasks. That data processing is also generating a lot of metadata with it. So for every I/O that's incoming, there are also multiples of metadata transactions that are taking place. So we need a metadata store to go with it. So these two workloads are the workloads that we're addressing, the write buffer cache and the metadata cache. And let's look at some key characteristics of these workloads. So when we look at the key characteristics of these two workloads, what we see is that for both of them, we really want the highest performance possible. And we're looking at the hierarchy of memory to storage. What we want is for these two workloads to have the same performance of memory of the top tiers here, but at the same time we want them to have the persistency of storage, which are the bottom tiers here. So these two workloads really fall in between these layers into what we call the mission critical, the performance gap between these storage and memory layers. So how would you address these challenges? So naturally, you'd go and say, let's use SSDs for that. And really in a few years, if you look back a few years, that's what most storage system would do. You take an SSD and you use that for the write buffer and metadata cache. But as we progressed and as flash became the predominant storage medium for storage, we are moving towards a higher IOPS range where these SSDs really cannot cope with this performance. And the key challenge here is endurance. Looking at the endurance required for this workload, and this is what you see here in the x-axis of the chart. Going from left to right, we're going from 50K IOPS to 1 million IOPS, and we're mapping on this chart the endurance level that's required to sustain that IOPS level. So if a few years back, a 50K IOPS system would be a very high-end system, today that's not even an entry-level system, and we have to look at 100K and above. For a 100K IOPS system, let's take that as an example, and let's say you want to use 400 gigabytes of SSDs. And that's the blue line that we see on this chart. As you can see, the endurance required for 400 gigabytes is 100 drives per day. Obviously nothing that a flash can sustain. And even if we double or quadruple that capacity, only then we get into the range, that 10 drives per day range, which SSDs can really sustain. Going forward in time, we are going towards that green spot on the right-hand corner where there's really no SSD out in the market that can sustain this workload. So clearly, from an endurance point of view, flash is not a solution for these workloads. So without flash, most people would look back and look at DRAM. So can we use DRAM for that? So obviously, from a performance point of view, DRAM is perfect, but the obvious the efficiency of DRAM is susceptible to power failures. So we have to protect that DRAM. And what most people do to protect the DRAM is they put batteries. They put UPS systems or battery backup units integrated. And these batteries bring with them a whole set of issues all by its own, right? Batteries are notoriously unreliable. Their lifespan is not as long as the system. So they create a maintenance issue, basically a maintenance nightmare. In addition, batteries take space. If you look at the rack of a storage that's backed up by batteries, a quarter of the rack is taken by the batteries. Clearly, we could do something better than use that rack space for batteries. So when we look at this problem space, we came up with our NVRAM drive, which fills in the gap, and that's the gap in between the memory and the SSD tier underneath it. And with the performance that we bring with our NVRAM drive, we believe we not only fill the gap, but we also bring in a few unique features that I want to spend a couple of minutes on. To begin with, and this is what you could see just by looking at the hardware, this is a standard form factor PCI Express. It's a low-profile, half-length PCI Express, very compact design, can fit into any server, practically universally compatible with any server. In addition to that, we also bring some innovation to the interface layers on top of this solution towards the host layer. If you look at these slides, you'll, from the left side first, the native interface for applications today would be a block-based interface. So we provide an NVMe interface, which is a native interface for applications that have been using block devices forever. So that's an easy integration point for current applications. And this is also a native interface for the write buffer cache, which is using large block data going in and out of this buffer. In addition to that, we provide also the memory mapped access. And in this mode, we take the memory capacity and we map it directly to the virtual memory address space of the application. So when the application has to access it, it is accessing this memory as native memory using CPU load store commands without going through the storage stack, without going through any software or driver layer. And that's a very native way for applications to access memory when it's used for metadata applications. So with these two interfaces, the block-based interface and the memory map interface, we cover both workloads that we started with. We cover the buffer cache workload, we cover the metadata workload, and we address these two needs in one solution. Let's take a look at the performance that we can provide. Obviously, we can provide the endurance required, but in terms of performance, you can get 1 million IOPS out of this NVRAM drive. And if you could compare that to SSDs, and the key here is to compare that with a sustained level of performance from SSDs, we're 10 times better than any SSD out there. And we, in this slide, we compare it to state-of-the-art PCI Express SSDs. And the key to remember here is that SSDs basically rely on flash. So you could get peak performance out of flash, but on a sustained level, flash has the endurance problem, and you simply cannot get this level of performance out of flash. And it's also asymmetric. So we provide symmetric performance, 1 million IOPS reads and writes on a sustained basis with no endurance issues. Now that's for the NVMe interface. Let's take a look at the memory map interface. In the memory map interface, our performance goes way higher than that. We can sustain 15 million random write IOPS at 64-byte resolution into this device. So as I mentioned earlier, for every data buffer that we handle, there are multiples of metadata IOs. So if we can sustain 1 million write IOPS, we have to sustain multiples of metadata IOPS. And with 15 million random write IOPS, we have plenty of headroom to go with this solution. And finally, the last performance metrics that I want to share with you is the CPU utilization. Comparing this with a memory-based solution, the key advantage that we have as an NVMe drive is the efficiency of doing DMA transactions And NVMe as a protocol is very, very efficient in doing that. So moving the data across from a memory to our NVRAM solution using NVMe, we are 4 times more efficient than using CPU cycles for that. And that's something very important to remember, that if you're just doing memory copy and you're basically using CPU cycles which could have been used for application processing, which is what CPUs were meant to sustain to begin with. So that's in a nutshell our key performance characteristics, and with that I'd like to conclude and summarize our key performance and benefits. We believe that with the NVRAM drive we are establishing a new storage tier and a new performance tier in between the DRAM and storage with over 10 million write IOPS and 1 million IOPS for 4K blocks. We provide the performance and endurance that applications need. With our industry standard interfaces, our form factor, our PCI Express form factor, our NVMe drive interface, and our native memory map access, we provide faster time to market and lower cost of ownership for the system. And in addition to that, we are also designed for enterprise class mission critical applications. So we have the reliability built into the design for a 5-year lifespan that's required for our customers. Thank you for your time, and we'll see you at our next show.